Okay, so this is from your lecture last night. What parts in this section right here did we not get filled in? So this should have been the night before, evaporation and vapor, right? Then we got down to boiling point and boiling point. Any problems with boiling and boiling point? Going over the other page, just defining what boiling point is, what normal boiling or standard boiling point is, and what happens to boiling water in a pressure cooker as the pressure is increased. What happens to boiling point if the pressure is decreased like it does in the high mountains? Any problems there? Okay, melting or subliming. Any questions with what you needed to pull out there? Okay, then we get to our heat curve, and this is where last period had a lot of problems, a lot of questions. Okay, so do we have any questions here? Okay, so let's look at this. A to B, what's happening? What's happening A to B? You're heating a solid. What's happening B to C? Melting. You're doing a phase change. What about C to D? Heating a liquid. What about D to E? You're changing a liquid to gas. What about E to F? You're heating a gas. So every time that we have a slope, like here, here, and here, we're going to use the equation Q equals mCp delta T to find out how much energy is given off, because we're going to have a change in temperature. The problem comes when we hit the flat area, when we do a phase change. Okay, the phase change here is going from a solid to a liquid. We're not changing temperature, so we can't use that equation because that equation would always be 0. But we know it takes energy to melt a solid to make a liquid boil, right? So on this one, to get Q, you're going to have to use delta H of fusion times the mass or times the molarity. You have to look at what delta H is given to you in. If it's given to you in kilojoules per mole, then you got to have the MB in moles. If it's given to you in joules per gram, you can use grams. So you have to just look at what you're given. This is also a flat state right here where you're changing from a liquid to a gas, and you have to use the same type of equation here, but here instead of using heat of fusion, you're going to use heat of vaporization times the mass. Okay? We'll do some problems with that later, but that's easier for me to remember. Yes? So this could be mole. This could be either grams or moles, but it all depends on what unit the delta H is given to you in. Okay, so you got to watch that delta H, and if it's given in moles, then you're going to have to change your grams to moles before you throw it in. Okay? All right, let's go down a little bit farther. Specific heat. Did anybody have problems finding a definition with a specific heat?
Wait, what was number 2?
Number 2, I've got to go back and figure out. The graph is actually going over it, so I'll have to go back and look at that. I basically went through and picked out all the vocabulary that you would need, and I'm not sure what V is supposed to be there. Okay, so specific heat. Do we have a problem finding definition for specific heat? We're okay with that. Heat of fusion we just talked about. Going over to the other side, we got heat of vaporization we just talked about. And the equation for using specific heat. There are actually, the one that we used is the Q equals mCp delta T. This is where the other class wanted me to stop and go through these problems with them because they were not understanding it. Is that where you want me to do too? Okay. All right, so let's take these one at a time and go through them because you'll need to do some like it. Now, this is where you needed to use your book. The page number I think was a little bit different than what's up there, but it is in chapter 6. It is on page 201 where that is. So where that chart is that you need for that. And they want you to do it in calories. So it actually gives it to you in calories and it gives it to you in joules. So we're looking for a specific heat. And if I go through the equation here, or the amount of heat, Q equals mCp delta T. So for the first one, we need to get the specific heat out of the book for copper. So the specific heat for copper, if I'm looking it up here, is 0.093 calories per gram degree Celsius. Yes, ma'am. Kilojoules per mole, that is the heat of fusion of ice. Okay, so we're going to take and plug into this equation. So once we've got all the data, all we have to do is plug in. So the mass, 210 grams. The CP, 0.093 calories per gram degree Celsius, times by delta T, which is final minus initial degree Celsius. And that will give me the amount. I can go back and I can cancel out my units. Degrees Celsius will go out. Grams will go out. I'll be left with calories, which is what I want. Go ahead and throw that through the calculator. We should end up with 2 sig figs. $1,100, and that's calories. Did I have a second on that? Okay, so let me give you the CP for the others and see if you can do them, and then we'll come back together. So the water, steam, CP, is equal to 0.48 calories per gram degree Celsius, and the CP for mercury is 0.033.
Will we get these things on the test?
You'll get those on the test. They might be in a table, or they might be just given to you in the problem. Yes.
Where are you getting the CP?
From the table in the book. If it was in joules for gas, it would be 2.0. For mercury, it would be 0.14. So since they ask for calories here, and she likes calories, now these are not nutritional calories, these are lab calories. To get to nutritional calories, you'd need to divide these by 1,000. So I'm going to pause the video, work on that, I'll come back. Okay, so for those that wanted to practice this, let's see if we've got the same answer. I'm just going to ask for the answer here. What did we get for B? 9,600 calories. And what did we get for C? Okay, we need to make sure that we would show our work normally with the test that we're taking on the computer. You can't, but normally we would show that work. Okay, so the last one here, number 8, and we can go down to number 9 here in a minute. For solar energy to be effective, collected heat must be able to be stored. One proposal is that heat be stored by melting solids. And then when the solids solidify, they would give off the heat. How much heat would be stored by melting 50 kilograms of calcium chloride, melting point this, with a heat of fusion of this? Now remember, heat of fusion is delta H of fusion. So what equation am I going to be using here? So when I look at a problem like this is what I always do to start with, because sometimes I need more than one step. I always say, okay, here's my heat curve. Where am I? Okay, I'm right here at this flat part right here, right? So I can't use temperature. So they gave me temperature, I don't need it. Okay, they gave me more information than I needed. I just need to find Q at this point, delta H of fusion times by the mass. And I want the masses in the heat of fusion and the mass in my mass to cancel out, so I end up with an energy of joules or calories. So I have kilograms here and I have grams here. So I need to change that from kilograms to grams. How do I do that? Times by 1,000. So if I times that by 1,000, I'm going to end up with 50,000, right? Grams. Everybody okay with that? So down here, all I have to do is say, okay, 40.7 calories per gram times by 50,000 grams. The grams will cancel, and I will get what for my calories?
It is 203 million and
Okay, that's a big, big number, right? How about we put it in scientific notation? 2 point what? 03 times 10 to the I only needed 3 sig figs. So there's my 3 sig figs. So times 10 to the 6th, and that would be calories. Okay? All right, let's look at the next one. This is all you would see on a problem. Okay? I've broken it down in steps for you below. So I'm going to actually copy this onto the next page with the steps. But before we go there, I want to sort of say, okay, what's going to happen here? Calculate total number of heat in ice from negative 30 to 130. Okay, wait a minute. I got to do my heat curve again. I know that ice melts at 0, and I know that water boils at 100, right? And I am going from negative 30 right here, clear up to 130 right here. Everybody okay with that? So that means I am going to go through 1, 2, 3, 4, 5 steps to find out how much energy, because I can't just do one step to do the whole thing. Because each of those, the solid, the liquid, the gas, have a different CP. The heat of vaporization is different than the heat of fusion. Okay, so I've got to do 5 steps. So let's do the 5 steps. Bring it up. Okay, I'm going to draw my little graph again, just as a shortcut up here so I can keep track of where I'm going. I'm here at negative 30. Is that always? Yes. I'm going to 130, and I'm going to put in, here's my 0, and here's my 100. Okay, so the first step is to get the ice up to the temperature where it will melt. Anytime that I have a slope, I'm going to use MCP delta T. So I'm going to take and put, that's going to be here, Q equals, let's see, actually put it here, Q equals MCP delta T, Q equals MCP delta T, and Q equals MCP delta T. Well, I need the CPs. The CP for ice is I'm going to use joules this time, 2.1 joule per gram degree Celsius. The CP for water is 4.184 joules per gram degree Celsius. And the CP for steam is 2.0 joules per gram degree Celsius. Well, there's a couple other places I need to worry about here, so I'm going to go now to step 2. Step 2 is when I'm melting the solid, right? So I'm going to do Q equals heat of fusion times mass or moles, depending on what I'm given. And I do know that the heat of fusion for ice is 6.01 kilojoules per mole. And then this one right here, I'm going to do Q equals delta H of vaporization times the mass. And I do know that delta H of vaporization, and I'm going from memory because we tried to look it up last period, I think it's 40.3. It might be off on the, I know it's 40 point something kilojoules per mole. We're just going to use that so we can do the calculation. All right, so my red ones are in mole. So I want to change that 60 grams up here so I don't have to do it more than once of water into moles of water. And I know there's 18.015 grams. So let's find out how many moles we've got so when we start calculating, we don't have to stop. Should be about 3 point something. 3 moles of H2O. Okay, so that's how many I have. Okay, so I also am looking really quickly here at in the red and blue, comparing my energy of my unit of energy. In the blues, I've got joules, but in the reds, I've got kilojoules. So that means I'm going to have some big numbers in joules. So I need to convert those to kilojoules because I've got to add these all up, and they've got to be in the same unit to add them. So as I'm doing the blue ones, I need to make sure I divide it by 1,000 to get it into kilojoules. So let's start doing the first blue one. So Q equals mass, 60.0 grams, times the specific heat, 2.1 joules per gram degrees Celsius, times change in temperature. It is from the 30 up to the 0. So it's going to be 30 degrees that I'm changing. Degrees Celsius go out, grams go out, and I get an answer. And then I've got to remember, oh yeah, then divide that answer by 1,000 so I can get it into kilojoules. So what do we get for an answer before we divide it by 1,000 and after?
Before it is
Okay, and so after it would be 3.78, right? Okay, so let's do the red one. The red one's fairly easy. I got my heat of fusion right here. All I need to do is times it by moles, which we figured out up there was 3.33. Now, my moles cancel. And my answer here is equal to what? It's a little over 18, somewhere between 18 and 20. 20.01. 601 times 3.33. Okay, 19.837. I needed, you got 20, you got 20? Okay. So just 6.01 times 3.33. Okay. Well, at least we know what we did. Okay, that's good. So now we're going to do the next one. The Q here is equal to 60 grams times the specific heat, 4.184 joules per gram degree Celsius, times by the change in temperature. Now, this change in temperature is from 0 to 100. So I'm going to have 100 degrees that I go here equals. And remember to divide it by 1,000, and we get our answer. So grams are going out, degrees Celsius are going out. 60 times 4.184 times 100. You could divide it by 10 at the end instead of timesing it by 100. 25,104. So 25.104 kilojoules. Okay, I'm going to go the red. Next one. Again, it's fairly easy because I've already got moles up there. So I'm going to take that, times it by 3.33 mole. Moles are going out. This one will be bigger. Takes a lot more energy to change water into steam. I missed 0.2. Got it. Yes. This times these two. Okay, try it again. 40.3 times 3.33. Okay, yes. I think it's lowercase. I just write it. I don't know. Okay, next one. We're doing steam. So now we're doing from the 100 right here up to the top. So our change in temperature is going to be 30. So Q is equal to 60 grams times the 2.0 joules per gram degree Celsius times the 30 degrees Celsius. And we're going to divide that all by 1,000. I ran out of room, sorry, is equal to 3.6 kilojoules. Then all I have to do is add those all up, and I've got my total. And since we're moving from ice to steam, it's going to be positive. If we were doing the other way, it would end up being negative. Okay.
Can we keep all those numbers because
We actually should have shut it down because this one was to the, well, this last one. If we did, we should have grabbed some more here. 3.6, was it 0 after the 3.6? So we should take it down to just 2. So, whoa, hello. So we would cross that one out. That wouldn't be there. Let's try an eraser. That probably would help. That wouldn't be there. Because when we add up, it should be the last place they have in common. So the tenths, the hundredths, or the thousandths is only in a couple of them. The thousandths is only in a couple. So we would go to the tenths. Yes.
on the test today, will we be given CPUs?
Yes. Now she usually only goes through maximum 3 levels. So you would neither go from like a solid to a liquid, or a solid that's changing phase to a liquid that's trying to boil. So you have a maximum of 3 areas. No. But I wanted to do all 5 to let you see how it would work. But you can start at any place on that heating curve. Okay, yes? What I do is I always do the absolute value, and then I have to think, okay, is it giving off energy? If it's giving off, it should be negative. If it's taking in energy, then it should be positive. But if you always do products minus reactants, or sorry, temperature final minus temperature initial, you'll end up with the right sign. Okay? All right, any other questions with this? Okay, I'm going to go through really quickly what we're going to do in lab, because there's a few adjustments that need to be made. So, and I do mean a few. Okay, so this is a heat diffusion device. It shouldn't take you more than 5-10 minutes max, as long as you watch and listen and understand what you're doing. So put the phones away, please. Okay, so the first procedure, we're going to knock that whole first one out. We're going to obtain some hot water, and you're just going to grab one of the plastic beakers over there and fill it with hot water. I'll turn this faucet on, the hot, and it takes a few minutes for it to get hot, but then you can just grab some hot water. You're going to grab a styrofoam cup. You're going to go to the back. You're going to weigh the styrofoam cup. So we change this first one from volume. We're actually going to mass the cup. We're going to get a mass of a cup right here. And then we're going to use the other beaker that has the hot water to pour in about another 100 grams. It does not have to be exact. Pour in about another 100 grams, but you do need that mass right there. Okay? So you do need that mass. This mass of the cup and the water. Then after the whole experiment's done, before you dump this cup out, you're going to get the mass of the cup, water, and the ice that was melted. So this is after. So I'm going to split that line right there. And then this would be, you're going to have to get two differences. One is just the mass of the water, which is going to be about 100. And the other one is going to be these two right here subtracted from each other. So you can get the mass of the ice, because you're going to need that. Okay? So what you're going to do is you're going to go get your hot water. You're going to, after you get your hot water, on your way back, you're going to get one small little plastic beaker full of ice. Pack it in there pretty good, because if you don't get enough ice, you're not going to get a good result. You're going to grab your temperature probe and your Easy Link, and if you need to borrow one of my calculators, do. Make sure to hook up the Easy Link to the temperature probe first, then put it to the calculator. You're going to get your initial temperature of your hot water. Then you're going to dump the ice in. You're going to stir it until the last ice is gone. And it's really important you get the temperature right when the last ice is gone. Because if you wait, the temperature will continue to go down, because now it's heating the water up to meet the water that was already in there. And we don't want that. We just want how much energy is used to just melt the ice. Okay? We're just looking for the heat of fusion. So then once you get all that done, you go back and you measure how much you have total, so you can get how many grams of ice you put in. And then you're going to go do the calculations on this side. Okay? Questions? When you're all done with that, then we'll go back and talk about the quiz that you had some questions on and go over that. Sound good? And then we'll do the exit quiz. The exit quiz is only 5 questions. So it's pretty fast. Okay, go. Yeah.